then I can put it on the thing. All right. So back to Google Earth. Oh no, did it erase it? It did erase it. Okay, so let's just quickly draw this again. So if we consider this, we have this phenomenon I just mentioned where you have this plate and it's roughly that size and it's colliding with North America. And then up and down the coast, you have these active volcanoes, Mount Rainier, Mount St. Helens, Mount Hood. Those are volcanoes, everyone. Mount Adams. And then those give way to some dormant volcanoes. Mount Shasta, Crater Lake. And the reason I like this as an example is because what you're witnessing is the disappearance, essentially, of a plate. If you could imagine going back in time, some, I don't know, couple 100 million years, maybe not even that far, 50 million years, the Juan de Fuca plate would have been that big. The Juan de Fuca plate would have been colliding with North America, being subducted at some level. That subduction zone would have resulted in some ocean crust melting. That ocean crust would have made its way through the North American continent, and you would have ended up with two volcanoes, Crater Lake and Mount Shasta, that were active. But that crust is now gone. And so those volcanoes are no longer fed the active magma, which makes up the volcanoes. And so they're dormant. Okay, so in this picture, the Juan de Fuca plate would be this ocean crust being subducted and coming up through the continental crust. So if we fast forwarded like 50 million years, then what we're going to slowly see is this Juan de Fuca plate just slowly disappearing. Okay. And it's going to slowly disappear until there's nothing left of it. So as it disappears like this, then the volcanoes in Oregon are no longer going to be active. They're going to be dormant. And eventually, the entire plate will disappear. At that time, the only thing left will be the remnants of once active volcanoes. So I like this example because, again, it gives you an idea of the past, what happened in the past, and you can almost imagine what's going to happen in the future in Washington State. Now, something similar happens when we have a collision of two ocean plates. So in this case, the continent is at some distance away. So that continental crust is not interacting with this ocean-to-ocean convergence zone. When you have an ocean plate colliding with anything, you will have subduction. That ocean crust is pushed under. And now the melting is not making its way through a continental crust. The melting is making its way through the ocean crust. It starts at the bottom of the ocean as a volcanic vent. Eventually, the lava that is piling up on the bottom of the ocean will pile up to a point that it actually sticks out of the ocean, like the top of the ocean, the water. Once it starts sticking out of the ocean, you have an island. On that island, you will find earthquakes. You will find a volcano embedded within a mountain range. Good example of that is Japan. So if we cruise on over here to Japan, we'll find along Japan, we will find the presence of lots of mountain ranges. Got to get this back to north. We will find an ocean trench. The ocean trench is the indication that there's subduction taking place. There's your trench. You will find on the Japanese island, you will find volcanoes. Mount Fuji is a good example. And those are active volcanoes. So I should make this red. That is an active volcano. And you will have lots of earthquakes. Okay. So the only difference here really is the formation of the island chain. And so when we talk about ocean to ocean collisions, one of your biggest clues that there's two oceans interacting there is the presence of that ocean chain. If you move up and down kind of the north to south here from Japan, you will see the presence of several of these ocean trenches, and you'll see the presence of lots of different island chains all the way through the Philippines, all the way down into Indonesia. And those all represent that ocean to ocean plate boundary. Okay, so then what about two continents colliding? So now you have continental crust made of granite, another piece of continental crust made of granite. Keep in mind the granite is relatively less dense than the basalt, so you're not going to have a subduction zone. And instead of the plate moving into the earth, the plates are going to fold and mostly build upward. And so when we see two continents colliding, this folded mountain range is going to be very common. And that folded mountain range is not going to include volcanoes. And so the best example of this is the collision of India with the Eurasian plate. And of course, at that boundary, we have the largest, the highest mountain range on the planet, the Himalayan mountains, including Mount Everest, which is the highest point. And so this is very typical. Within the Himalayan mountains, you have earthquake zones, and you also have very high folded mountains. Collision, the rock actually folds, twists, turns, and crumples. Okay. Now notice in the examples here, of course, you have the Himalayas, but you also have the Appalachian Mountains. So I want to take just a minute here and consider what is going on with the Appalachian Mountains. So running from Maine down through Georgia, you can find in the United States an old mountain range. And that old mountain range is folded, comes all the way down through here. It's on the coast there. It's folded. That mountain range, you can tell it was pretty high at one time, and there are no volcanic remnants. So where is the continent that was colliding with the east coast of North America to form the Appalachian Mountains? Where's that continent located? Think for a moment and just kind of look around a little bit. Do you see it? Well, as it turns out, plates can move direction. They can change direction. And so we believe somewhere around 200 million years ago, Africa and North America were joined, and the plates that joined them actually were moving together. So if you examine Africa today, you will find a similar mountain range right up in this area. Similar mountain range, similar age of the rock, similar rock formations. And it's believed that at one time, North America and Africa were joined and actually actively moving into each other. And based on the age of the Appalachian Mountains and the current height, it's believed that at one time, the Appalachian Mountains would have been a higher mountain range than the Himalayas are today. As soon as you change direction of the plate movement, you end up with what is called a divergent boundary, and those plates begin to move apart. Today, we see that moving apart continue, and the landform that results from it is known as the Mid-Atlantic Ridge. It's going like this. The Mid-Atlantic Ridge is a divergent zone. And again, this is a counterintuitive one. So when students think of divergent zones, they imagine a valley opening up where those plates are moving apart. But in fact, what happens as soon as that crust gets sufficiently thin, where that divergent boundary is located, Then magma, liquid rock from inside the earth, under great pressure, begins to flow upward through that weak crust. And eventually it is extruded onto the surface. We call that lava. And it begins to form a ridge. So where the crust gets thin, that represents an opening for new crust to be formed. That happens very obviously in the Mid-Atlantic Ridge and also in one other place on planet Earth. Before we leave the Appalachians, though, I want to mention one last thing. So you have that divergent boundary in the middle of the Atlantic Ocean. This large mountain range, which represents the Appalachian Mountains, as soon as that plate movement changes and instead of a convergent boundary, you have a divergent boundary, then that rock, that mountain that is above the surface of the earth, that begins to weather and erode. As soon as you take any rock and you lift it up into the air, then the processes of weathering and erosion begin to act on that rock. And so ever since that divergent boundary began to form between North America and, well, what is now North America and Africa, then the only processes acting on the Appalachian Mountains has been erosion. And if we return in another 100 million years, there may not be an Appalachian mountain range. It will be eroded to a point where it will be maybe just a plain. I want to point out one other divergent boundary. We just talked about the Mid-Atlantic Ridge, and that is in Africa. And so again, I like this as an example because the Red Sea and the Gulf of Aden and that Ethiopian highland area, that represents the formation of the next great ocean. So at one time when North America and Africa were together, you had that divergent boundary forming. You would have had a shallow sea, which eventually over tens of millions of years has given way to the formation of the entire Atlantic Ocean. You're seeing that same process happen here in Africa, but we get to witness just the very beginning of it. And so if we came back in another 500 million years, 200 million years, some point in the future, what we would witness is the next great ocean. And that great ocean would be forming right in this region right here. So the Red Sea today is a big sea, but fairly small, relatively speaking to oceans. That will not be the case in another 50 to 100 million years. You are seeing the next great ocean form. And the Horn of Africa, by the way, this most likely will be ripped off of Africa completely and become an island. And there'll be an ocean between the two. So I like that as an example because, again, you know, we live on this planet that is dynamic. This planet is ever changing. And once you understand plate tectonics, you can begin to look at the plates and the directions they're moving, and you can begin to predict where they're going to be in the future. And when you look at this part of Africa, you can see the next great ocean forming. The last type of plate boundary is a transform boundary. And transform boundaries are not moving into each other. They're not moving apart. They just slide past each other. And the most common example of this is right here in the United States. It is the San Andreas Fault. And when you consider San Francisco and Los Angeles, they actually exist. They're located on two different plates. And those plates are slowly moving toward each other. So someday in the future, San Francisco and Los Angeles will be suburbs. It's true. The most common landform or event associated with transform faults are earthquakes. You can get some rippling in these areas, but mostly they are located and identified by the presence of earthquakes. Keep in mind, earthquakes are present for any of these boundaries. Anytime you have rock moving, you will have some sort of earthquake. This diagram just sort of wraps it all up and puts it all together. So that's it, everyone. That's basically plate tectonics in a nutshell. And keep in mind, your task is really just taking these interactions, what direction are the plates moving, what kind of crust is involved, and then predicting the landforms that might originate. Okay, now everyone, I want you to take a deep breath, and I want to do one other thing here quickly, because very commonly in science, as soon as you have a theory or an idea, of course, then there's an exception. And so I want to examine this exception here for a moment and describe to you this phenomenon known as a hot spot. And one of our states, Hawaii, represents a hot spot. And so if you examine this area here, this is the Pacific Ocean. This is the Pacific Plate. And we know outlining the entire Pacific Plate are lots of volcanoes, lots of earthquakes, and they run right along that plate boundary, kind of like that, and all the way down and around. But then we have this weird phenomenon where we have the Hawaiian Islands, which we know are volcanic in nature. And very commonly, students think, well, that must be or represent a plate boundary. However, something different is happening here. And we call this a hot spot. So if you think back to the diagram that I showed you that describes the convection currents inside of the Earth. Think there's any way we could find one of those? That describes the convection currents that are inside the Earth. I don't think we're going to be able to. I thought maybe I could grab one quickly. Not really, no. So a hotspot is one of those plumes of magma, but it's not quite big enough to create its own plate or to move its own plate, but it is big enough to burn its way through the ocean floor and create an island. And so if we went to the bottom of the ocean, just off the coast of Hawaii, we would see sort of an interesting phenomenon. What we would see is that there's an active volcano actually just off the coast of Hawaii. It would be located right over here. And that active volcano has not quite popped itself out of the water yet. There's also active volcanoes right here in Hawaii. But then as we move to the north and to the west, what we find is a phenomenon where the volcanoes are not active. They are inactive. Also, the rock gets old. So this, let me do this in a color that shows up. This represents the newest crust or the newest part of the island. And this is the oldest. So I want you to think for a second, what is happening at this location? What is happening at this location within the interior of a plate where you have new crust and new islands on one side and older rock, dormant volcanoes, almost in a line on the other end of the island chain? What do you think is happening? Well, that plume of magma is rising right here, okay? There's a plume of magma rising, and as that magma rises and makes its way through the ocean floor onto the surface and then eventually builds up and creates an island, the plate is moving. And as the plate moves, it drags the islands with it. As soon as that island is away from the hotspot, it is no longer under the active plume, and therefore it no longer is an active volcano. Then the only processes acting on that island is erosion and weathering, and the island begins to deteriorate until a point where the oldest islands are not even above the water anymore. These are the oldest Hawaiian Islands, and they are now eroded and weathered to a point where they're not even out of the water anymore. This is continuing to happen. So basically what that means, if you want to own some land in Hawaii, all you have to do is go off the coast and buy the Hawaiian island that has not quite yet peeked out of the ocean yet. And then your great grandkids will own some of the Hawaiian island. That's a hot spot, everyone. And again, it's an interesting one because you can see by examining the age of those rocks, plate tectonics in motion. Now, this is not an example of a plate interaction, but the plate is actually moving the Hawaiian Islands toward the north and the west. By the way, one last thing quickly, there is one other hotspot in our country, and that is Yellowstone National Park. Yellowstone National Park is considered a hotspot, and Yellowstone National Park, some people believe in Wyoming, is the next great volcanically active area that could erupt in the United States. We know it's erupted in the past. We know the eruption of Yellowstone is probably the last biggest eruption to ever occur in our country. And so if you want to visit Yellowstone, maybe don't wait, do it soon. Everybody, in chapter 8, you can turn this assignment in where it says plate movement and landform activity. There should be a place in there for you to submit this assignment. And then we're going to move into soils. On Monday, I'd like to go over this soil assignment right here. I'm going to share that with you now. I'm going to put that into the chat. You're welcome to start looking at that over the weekend. Let's see here. Where's the chat? You can open this, put your name on it, and make a copy, please. Also, in Canvas, if you want to get a head start, we're going to be going over some of these notes about soils on Tuesday. I have some notes here. I also have a couple web video tutorials. I have to warn you, one of the videos I made lots of these videos. One of them, this soil horizons formation, the audio is terrible. I had this horrible mic and it is terrible, terrible audio, at least at the beginning of the video, but it gets better. But still, that video has over 100,000 views. Isn't that funny, you guys? I have a video with over 100,000 views. I'm not bragging right now. I'm just saying it is, even with bad audio. Did anybody have Mr. Strauss? Mr. Strauss loves doing videos.